Okay, I'm not cover this topic yet, right? Saya tak cover lagi kan topik ni. I don't remember. Okay, good. All right. Capacitive transducer. Okay, this is the second last topic. All right. Typical instrumentation system. This is what we have known before. So transducer, and then we have the signal conditioning, analog to digital, and also display. Okay, and what happened? Okay. And the transducer, as we know that it can be, it can convert from mechanical to electrical signal. And transducer, sometimes we can call it as a sensor. Okay, so it can detect the physical signal like temperature, and then it can convert into electrical signal. And there are one words which is actuator. I think this one you already know. It can convert from electrical signal to physical parameter. Okay. Transducer can be divided into two categories, which is passive and also active. Okay, all right. All right. Let's look at what is the capacitive transducer. Okay, capacitive transducer is consists between two plates. All right. Okay, sorry guys, I don't know why it's lagging. My computer is lagging right now. Okay. All right. So it's quite simple. It's consists two we call it a moving plate here, right? So this is your moving plate here, and then so there are dielectric between is this moving plate. Yeah, this is dielectric. So you got it, this dielectric. This is the moving plate here. All right. So of course the uh, the output of the capacitor is quite simple. It will give you the capacitance, all right, and then it is depending on your displacement D. So the formula for capacitance is give you this. It will proportional with the dielectric and also the surface area between these two plates, right? So this one is dielectric, PR, and also it will inverse proportional with the distance, this one D. Okay, and of course you will have some dielectric constant here, which is dielectric constant is equal to 8.85 picofarad over meter. So we know that this is the transfer function or sensitivity of the transducer of the capacitive transducer. That means the output will be capacitance and also the input will be displacement millimeter. Okay, it's not about only the square plate right here. There are some example if you have a two-cylinder plate like here, right? So there are one the big cylinder here and also one the smaller cylinder here. So as long right there is two metal plate, right? Two plate, right? So and then you will have your dielectric constant, right? So the application of the capacitive transducer is a lot. So it's like in your car, like the sensor to measure the level of your petrol, right? So that's one use the capacitive transducer. Okay. How to measure the capacitor? There are three variations. So first of all, you can play around with the distance here, right? With the distance. So you can move your plate, right? Maybe this one is constant, and you can move up and down here. So you can play around with the distance here, and then of course you will get the variation of the capacitance. Okay, and the other one is you can play around with the area. So this is the area, right? This is the area that connected to the dielectric. So this one area, right? A. Okay, and then you also can play around with dielectric constant. So there are three variations depending on the application, right? This show that you play around with the distance. This one you play around with the area, and this one you play around with the dielectric constant. Okay, let's look when you play around with the distance. Okay, so when you play around with the distance, that means this is your initial distance, and then your plate, right? The upper plate is moving up, so that means you will added something a certain distance like that. So that means your capacitance right now it will become C equal to ER E naught, and then A, all ER and A is constant, right? You not change on that. The only change is the distance, X. So your capacitance value, if your X will increase, that means your capacitance will decrease. Okay, right? Okay, this is the, one example. Okay, so moving to the right, okay, moving to the right. So that's mean the area, right, they attached to the dielectric constant, it will be a little bit less before that, the areas before. So on what you will have right here, dielectric constant, you will not change, right? And then A minus omega Wx. So where is your Wx is the width you time with your x. That means you will got it something a new area here. So A minus with the new area here, and then D is your constant. All right. So when you have the less area, that means C your capacitance will also will be decreased. Okay, so WX. So this is the variation when you play around with the area. Okay. All right. So let's look another. Uh, okay, another. Okay, the third variation. Oh, okay. Why is lagging? I think because of the. Uh, okay. The third variation is you constant the area, you constant the distance, but you play around with the dielectric constant. Okay, so dielectric constant here. Sorry, guys. Okay, all right. Okay. Now, if you look into that, there are when you play around with this dielectric constant, actually there are two capacitance there, C1 plus C2, where your C1 is I can put it is E1, right? E naught A A1 plus D, okay, and then A2 A naught. So that's mean you got it is A2 divided with D. Okay. So where is your A1 right here is it depending, right? So A1 that's mean X you time with your W, that will produce the A1. And also the A2 that's mean the length, right? The initial length you minus with X, then you time with your W. Okay. Then after that you can simplify this equation, right? To be like divided with D, then you play around with E2L minus E2 minus E1, and then we time with X here. Okay, right? So this is where you what we call it simplify the equation. But basically there are two capacitance there, C1 and plus C2, right? And then the C1, the area, right, that attached to the E1, right, will be X you time with W. And also the area for C2 will be L minus X you time with W, basically, okay? All right, so far do you have any question? Okay, ada apa-apa soalan tak? Okay, all right. Okay, so let's look example 8.1 here. Right. Figure below show a capacitive separated by a plastic shell or bearing of thickness 1 mm and dielectric constant at 1 kilohertz of 2.5. If the radius is 2.5 cm, find the sensitivity in picofarad per meter as the upper cylinder slide in and out of the lower cylinder. Okay, as we know that the capacitive transducer, the output will be capacitor and also the input will be meter lah. So before that I put it millimeter, but actually for the standard value is the meter. So the what we call it, the sensitivity or transfer function picometer per around picofarad, right? Farad per meter. Okay, the unit for capacitance is farad. Okay, so you got it two cylinder here, one the big cylinder and one the small cylinder, and then it separated by the placement of D here. All right. So you want to find the sensitivity, that's mean picofarad over meter. Okay. All right. So let's look the solution right here. Okay. First step, what you need to do is, so you gather all the information first. Now you got a dielectric constant equal to 2.5, and this one we know the dielectric constant is 8.85 with time with 10 power of minus 12. Uh, the unit will be farad per meter, and then for the radius for the cylinder is 2.5 centimeters, so we convert it into meter right here. And then from this one, we can get the distance between the two cylinder is divided into 1 millimeter. So this one will cost you 0.01 meter like here. And then as we know that the area for the cylinder is 2 pi r h like here. And then we can get it, the formula for capacitor is ER E naught area over D. This is the standard formula. Then what can we got it here is A is 2 pi RH divided with D or C. And we can find the DC over DH right here. All right. And what can we get it here is ER E naught and then 2 pi r over D. Okay. So DC over DH will be your sensitivity, right? Sensitivity, right? DC over DH. Yeah. Okay. And we can step 1. And then you can have the step 2, right? For sensitivity. Sensitivity. So we can put it DC over DH. ER E naught 2 pi r over D. Okay. So from here, so you can put ER is 2.5. So your E naught, okay, 2 pi, and R is your 0.025 divided with D 0.001 meter. Okay, okay. Then you can get it your sensitivity is 3475 picofarad over meter right here. So that means your sensitivity right here is 3475 picofarad over meter. Alright. Okay. Alright. So far, do you have any question? Ada apa-apa soalan? Boleh dengar tak ni? Do you have any question? Okay. Alright, good. Thank you. Steve. Okay. Now, after that, the question asks, what is the value for H that move from 0.01 meter, okay, 0.01 meter, right? And then what is the value that move from 0.02 meter, right? What is the value? So 0.01 meter, you just time this one, you can get the capacitance. So this one, you will get it 34.75 picofarad, and 0.02, you times this one, you can get the answer. Okay, I think that one is straightforward, right? Okay, so you can get this capacitance value based on this the height. Okay, based on this question. All right. Okay. So let's move to another slide. Hopefully, my computer don't got any problem. Okay. Yeah, example 8.2. Okay, example 8.2, where you play around with the dielectric. Okay, dielectric. So the area and also the distance of this dielectric of the capacitor will be fixed, and then you just play around with the dielectric constant E1 and E2 here. Okay, a variable dielectric capacitor displacement consists of 2 squared metal plate, W equal to L, okay, equal to 6, and it's separated by 1 millimeter, 1 mm. A sheet of dielectric material, 1 mm thick of the same area as the plate can be slide between them as shown in figure. Okay, so the distance is 1 mm. Given that dielectric constant of E1 equal to 1 and also E2 equal to 4. Calculate the capacitance of the sensor when they input the placement. S equal to 0.5 and 2.5 and also 5 cm. Okay, this one is quite simple. Actually, there are two capacitance there. Okay, if you look at that, so now this is your E1, this is your E2, and then this is your length here. Okay, and then the distance between this one is this 1 mm here. Okay, and L equal to 6 cm here, right? And W is here equal to 6 cm also. All right. Then this is your F. Okay. So that means actually C equal to C1 plus C2, and C1 is ER E naught A1 divided with D plus ER, that means E1, E2 E naught A2 divided with D. So you got it, the E1 right here, That is the value for A1, A1, A0. A1 that's mean the area for this one. Okay, so that's mean X you time with W divided with D plus with A2, A0, A2 that's mean your L minus X. Okay, L minus X you time with your W divided with D. Okay, all right. So this is another method number one, or you can just straight away use that formula. That formula where you simplify your C1 and C2. So you got it here, L minus with x2 minus 1 divided with x. Okay, so this one, you can straight away use this formula. You get it, right? So this one for x equal to 0.5 cm or equal to 0.005 meter. So you can get your C straight away. Okay, for x equal to 2.5 cm, then you can get your C straight away from use this formula. And then for the rest is x equal to 5 cm, then you can get your C straight away from this formula. Okay. So far, is it clear? Do you have any question? I think it's quite simple lah. All right. C1 and plus C2. Ada apa-apa soalan tak? Okay, good, Siti. Good. All right, the next example is 8.2. The level of ET alcohol is to be measured from 0 to 5 meter using the capacitive system that's shown in figure below. The following specification define the system. So for air, the dielectric equal to 1. And for the ET alcohol, the dielectric equal to 26. Cylinder separation between that small cylinder and the big cylinder equal to 0.5 cm. And for the radius, that's mean the average radius, okay, equal to 5.75 cm. And the length distance along the cylinder is equal to L equal to the length, okay, all right. And the area is 2 pi RL. Find the range of capacitance variation in air and ET alcohol as the alcohol level vary from 0 to 5 meter. So for it asks you to find, okay, what is the value of capacitance for the air, all right? And then what is the value of capacitance for the ET alcohol, right? So this is the example for the capacity transducer that have been used in your petrol pump or in your car, right, in order to measure the petrol level. Okay. So example 8.2. Right. Okay. So first of all, you gather all the information first regarding the R, the length, D, and also the area and so on. And then you apply for a general formula for the capacitance, C equal to ER, A over D. So you apply this one. And then you start to calculate for the air, right? So dielectric constant equal to 1, and then you time 1. Of course, 0 meter, that means the capacitance will be 0 lah. Okay. For the 5 meter, you just apply L equal to 5 meter, and then you will got this value C. Okay. So that's mean for the air, the capacitance value will varies from 0 to 3,199.7 picofarad. And then for the ET alcohol, so you just change the dielectric equal to 26, And then for the 5 meter, you will got the answer. So that's mean for the capacitance range for the ethyl alcohol 0 to 83,131 picofarad. Okay, right. I think this one is quite simple lah. Right, for capacitive transducer. Okay, this one another example. Another example, if it doesn't give you the average radius, right? So what you can do is you can use another formula like here. Okay, so you can find the average radius for the capacitive for the cylinder. Okay, so I think for the capacitive transducer is quite simple to get it, as long that you can know about the standard formula, right? General formula for capacitive. Okay, uh, so you can find it like here. So C E naught ER to 5 uh, over with ln, right? B over A like here, and then you can find for X equal to 0.04 for the air, and also for the alcohol 0.04 for alcohol, for the constant equal to 2. Okay, so this is how you calculate for the capacitive transducer. I think you can go through for this example. All right, I think that's it for this chapter. Do you have any any question that you're going to ask? Okay, ada apa-apa soalan? Okay, regarding your test 2, right? Yeah. So for in B, we just use the formula given, or we need to derive. Yeah, you just use that the formula given. Regarding your test 2, right? The question number 1, I think there are some issues there where you cannot find the value from that table, right? Yeah, it's okay. There are some mistake there. All right. Regarding the value, right? So there's the answer from the schema. From the schema, they forgot to consider 2 pi there. As long that you can get the critical frequency equal to, I think, what is it, the value 30k, right? Okay, 30k. So as long you can get that value, so you will get, yeah, 30k, yeah, 30k kilohertz, 30k hertz. Okay, and then you can get the full mark on that section. Okay, as long you can get that one, right? For the question 2, don't ask me. So others lecturer who doing that type of question, not me. Okay, all right. So just concentrate on your final exam. For the mark for test 1, still in marking. That's I wait for others lecturer, right? To mark that type of that uh, her question, all right? It's not her question. Okay, it's not finished yet. So be patient. So I hope that you can focus on your exam. All right. And next week we will have another topic, which is strain gauge. Okay. All right. Any question before we stop our class? Herman, retest. Yeah. You want to have a retest? No. Okay. No. All right. Okay. I think topic for final. Yeah, that one will be later lah. Okay. I will give you. Okay. I think that's it for today. Right. I will see you again on next week. Right. Uh, that's it. I think. Assalamualaikum and good morning. Okay. Take care. Yeah. Take care to all. Right. Now Johor baru have PKP. Right. Okay. Okay. Ada new baru. Apa tu? Berita. Apa? Berita apa? New. New itu apa? Herman. Berita apa? Time to sleep again. Yes, exactly. Oh, I see. I've not seen that before. Okay. What is this news, Herman? Can you conclude on that? Oh, darurat, right? Until okay. All right. Okay, good. All right. Thank you. I see you again.